VLSos here. This is a video lesson on the mean value theorem. We had a lesson previously on how to calculate the mean value of a function, the average of a function. And the expression to do so is finding the area under the curve on an interval of a continuous function, or a function that is continuous on that interval, from a to b, and then dividing by the width of that interval. In this presentation, the average is found as a place in the domain C, such that if we put that value in, we can calculate a value of the function, which then would be the average. Visually, if we had a function, any curve, and we could find the area under that curve on the interval from a to b, then the area under the curve would correspond to the area of a rectangle whose height was the average value of the function on that interval. We have function values within the interval that are going to be below the average and function values that are going to be above, because the average is in between. The amount of area above the line that represents the average is going to be equal to the area that is below or between the average line and the function. So we fill in the area under the curve to make it into a rectangle. The rectangle's area is the base times the height, or the width of the interval, times the average value, which is how we got the expression to calculate that average value as the area under the curve, or the area of the rectangle, then divide by the width in order to get the height, or the average value. In this presentation, C is a location in the domain, and there may be more than one, that we would put into the function, and that domain value C, wherever it is within the interval, is then going to be the value of that you can calculate the average of the function. This presentation can be modified if we had the antiderivative of the function and applied the fundamental theorem of calculus. Then this definite integral could be expressed as the antiderivative of the function evaluated at the upper bound minus the antiderivative evaluated at the lower bound. That's simply applying the fundamental theorem of calculus to the numerator, the integral. But we're still dividing by the width of the interval, b minus a. In this expression for the average value, we're using a function. In this expression, we're using the antiderivative, or the integral of that function. So we could draw a visualization or a graph of the corresponding expression which calculates the average value of the function. In this case, the graph is going to be the antiderivative of the one that we've used before, if we call this the f function. And the antiderivative of this is going to be approximately how the area under the curve grows as we increase the horizontal variable. So we could see that we have an area of 0 at the beginning, and the area goes up, increases. It increases more quickly when we have this high part of the function, and then the area still increases but slows down. We can capture that nature with a curve that looks approximately like this. This would be the antiderivative, or capital F, of the graph above. The mean expression to calculate the mean that includes the antiderivative looks like a slope calculation. It's a rise over a run. It's the slope of the points, or it's the slope of the secant line that connects those 2 points. So if we have an interval from A to B, then the slope, or the average value of the antiderivative from A to B, is this slope calculation. The average value then is the slope of that secant line, and C would be any value in between the interval, and there may be more than one, where the slope of the tangent line to that point is equal to the slope of the secant line between the points of the endpoints of the interval, because the slopes are the same. The mean value theorem is this, abbreviated MVT. If a function is continuous on a closed interval, then there is C in that interval, but not its endpoints, such that 1 over b minus a times the integral from a to b of that function with respect to x is equal to the function value at that place C. In other words, this is capturing the idea in this first graph. If we have a continuous function defined on a closed interval from a to b, then there's going to be some place in that domain within the interval such that the average value, the value of the function evaluated at that place C, can be found by the expression 1 over BA, which is the same thing as dividing by B minus A, the area under the curve from A to B. The second presentation can be expressed, it's the second part, or is equivalent to the mean value theorem if you're working with an antiderivative of a function instead, and it is continuous, and differentiable, on a closed interval, then there is a place that we could say C within that interval, but not its endpoints, such that the antiderivative evaluated at that place, the derivative of the antiderivative evaluated at that place, which would then be the same thing as the function evaluated at C, is equal to the area under the curve expressed as the fundamental theorem of calculus divided by b minus a, or we could show it like this, 1 times 1 over b minus a. These together are the mean value theorem. It doesn't have two parts so much as there's two ways to approach it. One approach is with a function, and the other approach is helpful when you have the antiderivative or the integral of that function.